So in this topic, we focus on congestion management and congestion avoidance. Congestion management and congestion avoidance. So when a network is intermittently congested, key packets need to be forwarded with a higher priority. So congestion management is required. Now, we have different queue technologies and scheduling algorithms that are used to send packets in queues. Now, if a queue is full, some of the bursts and non-key packets or all subsequent key packets sent to the queue will be discarded. So for that reason, we also need congestion. Congestion management actually does not achieve that effect. So in this case, we need congestion avoidance. We need to use congestion avoidance. Now, how are congestion management and congestion avoidance implemented? And in practice, how are they configured? So those are some of the things that we should be looking at in this topic. So by the end of this topic, you should be able to, Owen?
Upon completion of this section, you'll be able to understand the implementation of congestion management, be familiar with common queues scheduling algorithms, be familiar with the disadvantages and solution of tail drop.
Of the tail drop, okay. So let's begin with why does congestion occur, or where congestion occurrence and the solution. Okay, so here, let's look at this scenario. So when the communication traffic between the headquarters and the branch exceeds the egress bandwidth of the headquarters, congestion occurs on RTA. So you see, from your network, you're having 10 megabits per second and 2 megabits per second. So that is 12 megabits per second. But here, you're only having 10 megabits per second. So congestion can occur there. Now, generally, congestion can occur in one of the following scenarios. One of them is rate not matched. Rate not matched. So packets enter a device through a high-speed link, then they are forwarded through a low-speed link. So that is what rate not matched means. Then aggregation. So for example, aggregation is you're having your LAN is connecting via 10 megabits per second, another 10 megabits per second, but your egress is just 10 megabits per second, like what we're having here. So if you aggregate all these packets that are coming in, then when they're going out, we are going to have congestion at that particular point. Now, the communication quality of delay-sensitive voice and video services may not be guaranteed. So, for this purpose, we need to manage congestion. Now, other than mentioning that, congestion can also have other adverse impacts on your network. Sorry. So some of these problems that might be caused by congestion includes it can really increase transmission delay and jitter. So we already know that, and we know that it's not good. It can also cause a lot of packet retransmission due to over long delays. So that's the other disadvantage. Then at number 3, it also lowers the network throughput. So that's another problem. The last problem is that it may cause network resources to be locked, or to go down completely. So for example, for network protocols, when we have overlong delays, it will cause route flapping, recalculation, and so on and so forth. So really, congestion is not something that you can tolerate within your network, because it can really lead to performance deterioration. So congestion management implemented through queue mechanism. So the solution to congestion management is a queue mechanism. So in the first step, what do we want to do? We want to put all the packets that are sent from an interface into different buffer queues, Then at step number 2, we now want to forward these packets in different manners based on the queue scheduling mechanism. So we're going to see several queue scheduling algorithms. We're going to discuss about them. Now, something else that I didn't mention in the previous topic is jitter. Jitter is actually reduced. Is actually reduced by use of a buffer. So if we don't want the differences in delays to vary so much, we want it to be consistent, then we can put packets in a buffer, then release them at the same rate. So one of the solutions to jitters is to actually put the packets in buffers. So please remember that. So again, congestion management implemented through these 2 steps. Please remember that. We put them in queues, then we forward from the queues depending on the queuing mechanism that we are using. Okay. Now, so how is congestion management implemented? In the last topic, we looked at packet classification and remarking, and we saw that we can actually remark either through simple or complex classification. Here we are using simple, so we are using the layer 2 header. As you can see, this is the same topology that was there in the last topic. Now, each of these priority is associated with a specific local priority, and thereby it's going to be placed on a specific queue depending on the priority. So for example, whoever has a local priority of 0 then goes to queue number 0 here. Is placed on queue number 0. So this guy came without any classification. So using best effort. If you've come with a classification of 1, your local priority is 1, and we place you on queue number 1. If you come in with a marking of 2, then your local priority is also 2, and we place you on queue number 2, and so on and so forth. So generally, that is how we do congestion management. So you send packets to different queues based on the mapping between the local priorities and the queue index numbers. So the mapping here is between the local priority LP and the queue index number. Now let's look at the next step. Now, local priorities are also referred to as internal priority. It's also important to remember that. So please remember that. Okay. So just an example here. So we have packets that are coming in. We have packets that are coming into the router. So we have voice packets, normal data, FTP packets, video packets. So for normal data, we take them, we place them on queue number 0. Manager data, we put him on queue number 1. Video FTP packets are queued on queue number 2. Voice packets are queued on queue number 5. Now, the main question here is then which queue is first scheduled? Which queue is first scheduled? So the call for providing differentiated services, diff survey, you remember, is to determine the forwarding sequence of packets in different queues. So queue scheduling mechanisms are used. Queue scheduling mechanisms are used. We have 5 queue mechanisms. So the first one is called FIFO or FIFO, first in, first out. We have PQ for priority queue. We have the WRR, which is weighted round robin. We also have weighted fair queue, and we also have class-based queue. So in the coming slides, we are going to look at how each one of them operates. So common queue scheduling algorithms. So we begin with FIFO. So this is the default, uses the best effort model, does not classify packets. Does not classify packets. So are you seeing that? Are you seeing that? So it does not classify packets. So the red packets here are very urgent. This one is secondary urgent, and then the yellow non-urgent. But it actually service packets on a fast in, fast out manner. So you see the yellow there, and then that one. So put them on the queue, then forwards them out in a similar manner. Now, the advantage for this kind of scheduling is that the implementation is simple and it does not require a lot of processing. Therefore, the processing speed is fast. Disadvantage, of course, is that packets with different priorities cannot be processed in different manners. So this is not very friendly to delay sensitive real-time applications such as voice and video. Now, the next one is called PQ. So PQ is for priority queue. Priority queue. So it defines a number of queues. So one with the highest priority, second highest, third highest, last priority. So let's see how it performs. So if we press next, you see if you're an urgent, you go to the bottom queue. If you're secondary urgent, you go to the middle queue. If you're top urgent, you go to the top queue. Now, let me just go back. Now, I want you to observe, after they have been added into the queues, I want you to observe here how they are forwarded, so that you can understand the main disadvantage of priority queue. So they're added to the queue, that is okay, like that, depending on your priority. Now look how they are forwarded. So we have to forward everything from the top queue, then the middle queue, then the normal, then the bottom. Now, this can be disadvantageous to low priority queues, which may not be scheduled. So whoever is on the bottom queue might not have a chance to be forwarded if we have a lot of traffic on the top or the upper queues, upper priority queues, let me call them that. So that's the main disadvantage. That's the main disadvantage of priority queue. The advantage, of course, high priority packets are preferentially forwarded. Kwa hivyo delay sensitive data zitafanya sawa kabisa. Zitafanya sawa kabisa. So that is how PQ. That is how PQ works. Now, an improvement of PQ so that we cannot starve the bottom level queue is what we call the weighted round robin. Weighted round robin. Just an improvement, by the way. So weighted round robin again implements different queues for different packets, but different from PQ. It implements a weight, a certain weight for each of the queues. So what this weight achieves is that it prevents the problem that low priority queues are not scheduled at all. So what the weight of 30 here means is, for example, we forward 30% of the data in this queue, then we forward 20% of the data in this queue, then we forward 10% of the data in this queue. Then we go around again. We go back to the top queue again, and we go back to QA, then B, then C. So we forward 30, we forward 20, we forward 10, like that. So that is how weighted round robin works. So we didn't have an animation for this. Okay, so you see, at least at the end of it all, we will have some packets from all the queues being forwarded. So we can't have guys from the bottom queue, low priority queues, not being forwarded. Disadvantage: packets are scheduled based on a number of packets. So in this case, packets with different sizes are not scheduled in a fair manner, and low delay services are not scheduled in a timely manner. So even though the weight here refers to the number of packets, percentage of packets that we can forward before going to consider the next queue, you see packets have different sizes. Packets have different sizes. So packets with different sizes are not scheduled in a fair manner. So if we have a queue that has very big packets, then we're still going to cause delays to packets that are on the other queues. So that is one of the disadvantages of weighted round robin. Weighted round robin. Okay. So other than weighted round robin, the other improvement to weighted round robin is what we call the weighted fair queue, WFQ here. Weighted fair queue. So with weighted fair queue, it allocates bandwidth based on weights. Then packets are actually classified automatically. And the configuration is very simple. So as packets are coming, are being sent to the interface, they're classified depending on their priorities. Then they're put on the different queues. Now with the weighted fair queue, the difference with weighted round robin is this one reserves bandwidth. It reserves some bandwidth for each of the queue. It reserves some bandwidth for each of the queue. So what happens really is when you're talking of Q1 here and the weight, so if this particular interface is a 1 gig, so this guy, for example, will take 30% of the 1 gig. This one will take maybe 20%, then maybe this one 10%, maybe this one 5%. So with that kind of bandwidth reservation for each of the queues, then it becomes actually possible to forward packets from every queue in a fair manner. So that's why it's called a weighted fair queue. Disadvantage with this is that low delay services may not be scheduled in a timely manner, and user-defined classifications. So it's not possible because it's done automatically. So user-defined classification rules cannot be provided. So that's one of the disadvantages of weighted fair queue, that it's done automatically. So we cannot be able to manually specify the classification rules. So please remember, the main difference between weighted round robin and weighted fair queue is that weighted fair queue reserves bandwidth for each of the queue. So everyone has some reserved bandwidth. Okay. Now, sometimes we can also combine two queues in order to combine their strengths and maybe also limit their weaknesses. So one of the possible combinations is combining the priority queue and the weighted fair queue. So what happens is in your system, you've defined Q0 to Q7. For packets from Q5 to Q7, you want them to be scheduled using the priority queue. And then for the remaining packets from Q0 to Q4, you want them to be forwarded based on the weighted fair queue. So when this happens, then you combine the advantages and also limit their weaknesses. So the advantage of this combination, for example, is low delay services are scheduled in a timely manner, and bandwidth is also allocated based on the weights. So these ones are very low priority. Lower. The priority for this queue number 0 to 4, they are lower compared to these ones. So these ones are high priority. So you want to forward them using priority queuing. But you're still not going to starve these ones because they are using weighted fair queue. So you can always combine those two together. Disadvantage, packets cannot be flexibly classified on user-defined rules. So again, we cannot classify, we cannot specify the rules to classify the packets into the different queues. So we've been talking of the disadvantage of you cannot be able to manually define the classification rules, and for that reason they developed CBQ, so class-based queuing. So the main advantage of class-based queuing is that it supports user-defined rules and defines different scheduling policies for different services. Defines different scheduling policies for different services. So the disadvantage of this is complex traffic classification is involved, and enabling CBQ consumes system resources. So generally here, you can decide that you have an expedite forwarding queue. You also have a number of queues that are what we call the assured forwarding queues, and some packets are also forwarded using the best effort. So really here, it is you as the network administrator that is actually doing these configurations. So those are the three types of queues that you can have: expedited forwarding, assured forwarding, and best effort forwarding. As we looked in the previous chapter, of course, when it comes to expedited forwarding, this is for highly delay sensitive services such as protocol packets. So I hope you remember, such as voice actually. For protocol packets, we said actually CS, the class specifier CS. Then for this one, AF, we also looked at examples, and we also have different levels. Then default, we also have the best effort. So if packets do not match any configured traffic classifiers, then they are forwarded using the best effort queue. So we have the comparison here between the different scheduling algorithms. I'll leave this to you as a reading assignment, so make sure you go through it. So let's look at the implementation of congestion management. So here we want to use PQ together with WFQ. Now we need to understand the requirement. So voices are forwarded preferentially and other services are processed in a fair manner. So we want voice packets that are coming from the enterprise headquarters are actually forwarded with a higher priority. Because see, we have a congestion point here. Because if we aggregate 2 Mbps plus 10 Mbps, then we have a possibility. It's more than this. You have a possibility of having congestion here. So that's why we need to configure voice to be forwarded preferentially. Okay, so how to do that is quite easy. So on this particular router, we want to define several queues, Q1, Q2, Q3, and Q5. Now, for Q1 to 3, we want to use the weighted fair queue algorithm. For Q5, we want to use the priority queue algorithm. So how do we configure? How do we configure this? So the command is QoS space queue hyphen profile, then the name of that queue. So you just give it any name there. Then you use the key term schedule. Then you specify PQ for priority queue. Then you specify the queue number. So Q5. So we want Q5 to be scheduled using priority queue. Then we use WFQ for weighted fair queue. Then we use the command 1 to 3 to specify that we want Q1 to 3 to be scheduled using the weighted fair queue algorithm. So after we've created this queue profile, we now need to implement it on the interface, on the ingress interface, G00. If I'm not wrong, let me just go back to the topology. Is it G00? Okay, they didn't show it. Okay, here, the egress, on the egress here, G0/0/0. So this is where we are configuring the queuing algorithm, the queues and the queue algorithm. So we need to implement that by using this command here. So QoS, queue profile, then the name of the queue profile that we want to implement on that interface. So with that, if we use the display command, display QoS, quality of service, queue profile, QoS-Huawei, which is the name of the queue we just created here, then we should be able to see these details. Should be able to see the name of the queue, the queue number, the scheduling algorithm that we are using, the weight of each queue, and other details there. So we can see that Q1, Q2, Q3 are done using a weighted fair queue. So weighted fair queue normally has weights, normally has weights for each of the queue, but for PQ does not have weights. So that is it about configuration of congestion management. You configure first the queue, then the queue scheduling algorithm. Now we are done with congestion management. Let's go to congestion avoidance. Now, traditional processing after the queue is full. Now, please remember that the queue can get full. The queue has a limited space. It has an infinite space. It has a finite space. So the queue length, the length of each queue is limited. So what happens when the queue is full? This is what happens. This is what happens when the queue is full. All subsequent packets sent to the queue will be discarded until congestion is eliminated. So this processing mode is what we call the tail drop. Tail drop. So let's look at this example. So we have 6 packets coming into this particular router, but the router per second, but the router in its queue, it can only process 4 packets per second. So what happens is that after the queue is filled, any packets that come in will simply be discarded. So it will only be able to process packet 1, 2, 3, and 4. Otherwise, 5 and 6 are going to be discarded. So remember that the queue length is actually limited, and this action of discarding any other packets that come in after the queue is full is what we call the tail drop. So what do you think might be the advantages and disadvantages of dropping the packets, these packets? So that's something that you're supposed to ponder as we move on. So the queue is full. When the queue is full, all subsequent packets sent to the queue are discarded. Now, tail drop might help to reduce congestion, but it also results to 3 main problems. The first one is called global TCP synchronization. Global TCP synchronization. The other one is called, okay, we are going to see it. Let's begin with global TCP synchronization. Okay, so we have 5 megabits per second there. We have 10 megabits. So those are 15 if you aggregate them. So when congestion occurs and the queue is full, packets at the end of the queue are discarded. So due to congestion, packets of a large number of TCP connections are actually discarded. So many packets there are going to be discarded. Now, what is TCP global synchronization? So far, we've agreed that at that point, at this particular point here, congestion can occur because the aggregated route here exceeds the rate at which this interface can forward data. So you now need to understand this phenomena called TCP global synchronization. So these are just TCP data. So that is a TCP data from one computer, this one from another one, and this one from another one. So let's see what is happening here. So TCP connections enter the slow start state. So low start state means that the queues are almost full and congestion is almost getting to the maximum. The queue is almost getting to the filled up. So that is what we call the slow state session. So as you can see, packets are coming in and the queue is almost full. Packets are coming in, TCP packets, and the queue is almost full. So what happens? Now traffic is heavy. As a result, the queue is full and tail drop is used. So let's for example follow this one first. So this one goes up to until the queue is full. So once the queue is full, because of these phenomena we call the tail drop, then we are going to discard some of these TCP packets. Now when we discard these TCP packets, the receiver or the server is not going to receive acknowledgement. As we know, in TCP, every packet we send has to be acknowledged. So for example here, the server is not going to get acknowledgements. When the server does not get an acknowledgement, what it does is that it reduces the window size. It reduces the window size, that is the size of the TCP packets. So when it reduces the window size, then this curve actually falls, because now the queue will have some space. But after it has actually fallen, someone else actually sends TCP data, and someone else again, and now these three TCP packets, you see, these three TCP streams, let me call them streams, also fill the queue. So again, what happens? Tail drop. When tail drop happens, again all of them will fall, because they'll reduce, the server will reduce the window size of the packets. So that will continue happening. Now what's the problem with that? So let me just clear this. So the TCP acknowledgement packets sent by the server are discarded due to congestion. So consequently, sender does not receive the acknowledgement and considers that the network congestion occurs. Then both the window size and the traffic are reduced. So when they are reduced, then we have this fall here, because now the queue will have some space. Now, network congestion is eliminated. At this point, we don't have network congestion. You can see we are below the upper threshold of the queue. Now the sender can receive TCP acknowledgement packets and consider that network congestion does not occur. So what does that person do? Then the TCP connection enter the slow start state. So this process repeats. So when this guy notices that the network congestion does not occur, they can again increase the window size. So that is why the graph will rise again. Now, this particular scenario is what we refer to as the global TCP synchronization. And now, what is the problem with this? The problem with this is that we are going to have this particular time when the queue is underused. And when we talk of the queue, remember we are talking of the bandwidth actually. So we are going to have these times when the TCP synchronization occurs, where we're not going to be utilizing the bandwidth. We're going to actually underutilize the bandwidth during these periods. So that is the main problem that is caused by the first disadvantage of the tail drop, global TCP synchronization. Now, one of the solutions to this problem is what we call WRED. WRED. So WRED is a very interesting concept. In full, WRED is random early detection. Random early detection. So that is what I call RED. So to avoid global TCP synchronization, some packets are discarded randomly before queues are full. So to avoid global TCP synchronization, some packets are discarded randomly before the queues are full. So the transmission rate of TCP connections can be reduced to prevent global TCP synchronization as much as possible. So such a random packet drop behavior is called random early detection. Random early detection. So let me explain using this diagram here. So here, this is the queue size. So this is the queue when it's 100% filled. So when it's 100% filled, what happens? Now, when the queue when the queue is not very busy, as what we can see here, when the queue is not very busy, then we do not have any packets being dropped. We do not have any packets being dropped. Now, when we hit a point called the lower drop threshold, drop threshold, now we begin randomly dropping packets, as you can see, and we will increase the probability of the packets we drop as the queue continues to fill up, like that. Now, when they hit the upper drop threshold, then literally from this area, we simply drop everything. We simply discard any other packet that comes after this. So we have the lower drop threshold, the upper drop threshold. So this is actually the actual queue length, and this is the maximum queue length. So when it hits the maximum, when it hits the ceiling at 100%, then we drop everything. Oh, now this is the drop probability when the queue is full. So we drop 100%. We drop everything. So I'm sorry, I had said that this was the queue size. It's actually the drop probability. So when the queue is not busy, drop probability is 0. When the queue starts filling up, the drop probability also increases exponentially. When it hits the upper drop threshold of the queue, then we begin dropping at 100%. At 100%. So I hope that is clear. So what happens? Or what happens here? I think this is what I've said. Okay. So what happens here is because we are using RED to randomly drop some packets here, then we are able to reduce the effect of TCP global synchronization. So the amount of time in which we reduce the amount of wastage that we were experiencing before. So that's the main purpose of random early detection, just to try and minimize the TCP global synchronization. So that's the solution to that problem. Now, other than TCP global synchronization, the other problem with tail drop is what we call TCP starvation. TCP starvation. So what is TCP starvation, and how does it occur? Now, let me begin by saying that TCP starvation is caused because tail drop cannot distinguish traffic. it simply drops anything that comes in after the queue is full. So my queue size is 1, 2, 3, 4. So anything that comes after that, I'll simply drop. So it cannot distinguish traffic. It cannot distinguish traffic. So what happens here? So sometimes you see with TCP, you have to receive the acknowledgement in order to continue to send. So sometimes when this happens, unlike UDP, with TCP, if you don't receive an acknowledgement, you cannot continue to send. So that means that if TCP acknowledgements, for example, are dropped here, then we are not going to be able to continue to send data. And therefore, for a long time, we might actually not send TCP packets. So that leads to TCP starvation. TCP starvation. So when the queue is full, a large number of TCP packets that are sent to the queue, and at the end, at the tail of the queue are discarded. So as a result, the window size and TCP traffic are reduced. However, UDP traffic is not reduced. Yeah, that's the other thing. UDP traffic cannot be reduced and may occupy the queue, so causing TCP starvation. Yeah, exactly. So I hope you understand this, that other than what I had said earlier, the real reason actually for starvation is this, that when we have delays in the network, or when TCP packets are discarded, then the window size is going to be reduced. But on the other hand, the UDP packets are not going to be reduced, so they're still going to be large. So that may cause delays in transmission of TCP packets. So that is what we are calling TCP starvation. Okay, sorry about what I had said earlier. So the other disadvantage of tail drop is drop without differentiation. Again, the reason for this is the same as what caused TCP starvation there. So the tail drop cannot distinguish traffic. So in a network, we have key data and non-key data. So TCP is not able to differentiate. So as long as the queue is full, anyone else that comes after that will simply be discarded. So how then can we cater for these problems that have been introduced to the tail drop solution? So tail drop may cause much non-key data to be forwarded, whereas much key data is discarded. So the solution to tail drop is what we call weighted random early detection. Weighted random early detection. So how does it work? So weighted random early detection sets drop policies for data packets with different priorities or queues to distinguish and discard traffic. To distinguish and discard traffic. So in this example, we can see that packets are placed into, for example, different queues depending on their priority. So different queues. So what happens if you have for example, if you have a higher priority, then we can set your drop. What did we call it? What did we call it? The drop threshold. We can extend your lower drop threshold. So you can see, for example, for the blue packets here, they can only be dropped after the queue size is remaining with a space of, for example, 35%. while the yellow packets will start randomly dropping packets from the yellow packets here when the queue is 30% empty. Then for these ones which are not very important from the green, we'll start randomly dropping packets from the green network, for example, when the queue is about has 30% at 20% space left, for example. Okay, I'm not sure whether I've used the correct explanation there. I don't know which is which. I'm sorry. Okay. So this is the actual queue length. So, okay, 20% drop probability. Then it's filled. Okay. It's actually correct. So, yeah. So, the thing is, this one is the first one that is going to be to start dropping. Then this one, then this one. Then when they hit 40, all of them, of course, will just be discarded because this is the maximum. So it's going to be dropped at the maximum of 100%. So this might mean something like, I'm just trying to, just as an example, 20% full of the queue, 30% full, 35% full, then maybe 100% full. Then we start dropping everything. So with this kind of differentiation of different packets, then the weighted random early detection is able to prevent the 3 disadvantages of tail drop, which is TCP synchronization, TCP starvation, and not being able to differentiate different service types. These enhances and greatly improves link bandwidth utilization. So that is what we call the weighted random early detection. Okay, so actually here is the explanation. So traffic with the IP precedence of 0, the lower drop threshold of 20, and an upper drop threshold of 40 is set. So 20 to 40. At 40, we start dropping everything from that particular queue. Then traffic with an IPP of 2, IP precedence of 2, like the blue one here. So the lower drop threshold is 35, upper drop threshold is 40. So we'll start randomly dropping. At 40, we start dropping everything. So such traffic is discarded later than the traffic with the IP of 0. So unaona hii wataanza kudrop later than here green. So I hope that is clear. Okay, so let's look at how to configure weighted random early detection. So the requirement, when the network congestion occurs and queues are full, we want FTP traffic to be discarded later than other traffic. So we want FTP traffic from the FTP server. We want FTP traffic from the FTP server to be discarded later than traffic from the other guys. Do we have any other requirement? Right now okay. So for the classification, we are using a DSCP, differentiated service code point. So we want to configure, I think we want to configure that on DS node, on this DS node. So it's not an edge node. SWA here is the DS edge node, and SWB, switch B, is also a DS edge node. But I think we are doing it on the DS node on G001. So let's see how to do that on RTA. So what happens here? Okay, just a moment. I think I need to. Okay, so I think the other requirement here is, other than FTP, we also want traffic from the manager network to also be forwarded preferentially. So we also want that to be forwarded preferentially. And of course, we also have voice data and video data, which also has to be forwarded preferentially. And then our data from the finance department, for example, can just be forwarded in the normal way. So those are the conditions that we want to achieve. Okay, so how to do that? So here is the planning table that we're doing. So we want voice to have a DSCP value of 40, a local priority of 5, and we want to place it on queue number 5. Queue number 5 is going to be scheduled using PQ. Then for video, DSCP value will be 24. That might actually be the default that is coming from that conferencing tool. Then the local priority is going to be 3. We want to put it on Q3. Q3 is scheduled using weighted fair queue. Then for FTP, the DSCP value, it's going to come with 16. The local priority will be mapped to 2. It will be placed on queue number 2, and we want it to be scheduled using weighted fair queue. Then you have the manager machine. DSCP value is 8, local priority 1. We want to place it on queue number 1, schedule that queue using the weighted fair queue. Now, after knowing that, the next thing is to consider the tail drop. The next thing is to consider the tail drop. So let's look at this. So here we have the video. You can see the first row here is for video. The second one here is for FTP. These are actually columns. And then the last column here is for the manager. So what we want to configure for the video, the lower drop threshold should be 60. So it's at 60 that we want to start randomly dropping packets, video packets. Then the upper drop threshold is 80. Then other than the upper drop threshold, we have the maximum drop probability. So between the low drop threshold and the upper drop threshold, we want to drop randomly a maximum of 20% of the packets. So that is what maximum drop probability means. So similarly for the FTP, lower drop threshold, upper drop threshold, in between there, we want to drop at a probability of 10%. The maximum drop probability is 10%. And lastly, we have the manager there. So how to configure that? We use the command drop profile. Then you give it a name. For example, manager. Then you use the command WRED DSCP. Then you say DSCP 8, DSCP 8, meaning that is the DSCP value. Then you specify the load drop threshold to 50. So for the manager, we set it to 50. We set the high drop threshold using the high limit there to 70. Then the discard percentage, which is the maximum drop probability, we set it to 10 here. So we can also create another one here. So here we are focusing on the FTP. So that's why you can see DSCP. So the value is 16, low limit 70, this one here, upper drop limit 90, this one, then the discard percentage is 10, like that. So after you've created for the manager, so here we were creating for FTP. This is the command, by the way. Sorry. Drop profile FTP. So we started with the manager. Sorry, let me just do that. So drop profile, then the name of that drop profile. Drop profile for FTP. Drop profile for video. So after we've done setting up the drop profiles, we can also create the queue profile. Can create the queue profile. So using the command queue QoS, queue profile, then the name of that queue profile. Then you say for Q1, use drop manager, drop profile called manager. So for Q1, use this guy. Use this guy. For Q2, use FTP. Use this guy. For Q3, use video. So use this guy. So that's what we're doing there. So after we are done, we now need to implement that on the interface by specifying the queue profile using that command, QoS queue-profile, then the name of the queue profile that we just created here, QoS-Huawei. So generally, that is how you configure the weighted random early detection. Ladies and gentlemen, that's the end of this particular topic. Asanteni sana. Any questions? Okay, thank you very much. Please take time and go through these questions in the next 5 minutes. If you are unable to understand any of these questions, please let me know. Asanteni sana.